Ladies and gentlemen, boys and girls, it's time to learn how to solve exponential equations with like bases. This with like bases part is going to be really important to us right now because our knowledge base on exponential functions and how to manipulate them and some other things is a little bit limited because we haven't started talking about logs yet. So when we get over to logs, this is going to look like child's play. Um, but the good news is that this really just uses a lot of mathematical know-how that we should already know. Haha. So, how do we go and solve an exponential equation that has a like base? Well, if we're going to do that, then there's a few things that we need to know. The first one of those things is mucho importante. So, and that is the following mathematical rule. If you have b raised to the x, and that has been set equal to, so it is an equation. So if b to the x is equal to b to the y, then x equals y. This is a similar concept to what you guys learned about in geometry, okay? You guys remember something called like CPCTC? Congruent parts of congruent triangles are congruent. Okay, and we could use that as a proof for congruent triangles. Well, you can use something similar in an algebraic context. So if the bases are the same, so they're already equal, then the exponents must also be equal if this equation is going to hold true. So it kind of makes sense. The other thing that we're going to need to remember, which may be a little harder at this point, is all of the rational exponent properties. So you guys have gotten a handout that you can use to reference those, but I've put the big three that we really end up using solving these types of problems down here at the bottom. So the first one, just to refresh your memory, this one is called the power of a power property. So if you have b to the x raised to the y, that's the same thing as b raised to the x times y, okay? Negative exponents, remember, they just kind of move it from being in the numerator to the denominator if we're trying to express that in the simplest way possible. So if you have b raised to the negative 1, that's 1 over b to the first. If you have b raised to the negative 2, that's 1 over b squared, etc. Okay, the opposite happens if your negative exponent is already in the denominator of a rational. So 1 over b raised to the negative 1 is b, or b over 1. 1 over b raised to the negative 2 would be equivalent to just b squared. Okay, so if we've got negative exponents, we should be able to handle that. And if we have power of a power that we can apply, then that could be a useful tool. So we're going to take a look at 4 example problems that are going to increase in complexity, and hopefully that'll help us get to a point where we feel confident in our willingness to try and answer some questions. So starting things off, we'll go with the easy route, okay? So example 1 is 7 raised to the 2x equals 7 raised to the 3x minus 5. Okay, so how can I tell this is an exponential equation? Well, the variables are all in the exponent, and I've got two things that are equal to each other. So, exponential equation. So the first thing that I need to remember is that if b to the x equals b to the y, then x will equal y. So let's look at this problem. What is your base that's on the left-hand side of the equation? It's 7. What's your base on the right-hand side? Well, it's also 7. So because those two bases are the same, guess what I can set equal to each other? I can set 2x to be equal to 3x minus 5, okay? Because my bases are the same. So 2x will equal 3x minus 5. Then I get to do just a little bit of arithmetic. So maybe I would subtract 3x from each side. So I'd end up with a negative x equals negative 5. But I don't want to know what negative x is. I want to know what positive x is. So multiply or divide both sides by negative 1. And you would end up getting x equals positive 5 is your solution for this. Okay, but one thing I'm always going to encourage you guys to do, check it, make sure it's right. So use substitution and probably a calculator. Okay, but we could go and say, well, is 7 raised to the 2 times 5 the same thing as 7 raised to the 3 times 5 minus 5? Well, I know that 2 times 5 is 10, so I got 7 to the 10th. That's probably a pretty big number, so I'm just going to leave it as 7 to the 10th. And then over here, 3 times 5 is 15, and 15 minus 5 is also 10. So is 7 to the 10th equal to 7 to the 10th? Well, yeah, okay. It's itself, so it has to be equal. So you can always go through and check by plugging in, but you might want to use a calculator to do it, because I'm going to guess that you don't happen to know off the top of your head what 7 to the 10th power is. Okay? I wouldn't either. I'm not that big of a nerd. Maybe I am. Who knows? All right. Anyway, let's go through and take a look at example number 2 then, because the first one, really easy. But why is the first one easy? Because we want you to see the process without getting bogged down in the arithmetic. So let's go look at number 2. Okay, example number 2 is 5 raised to the 4m, and that equals 125 raised to the m plus 2. And right off the bat, what can you tell? My first base of 5 is not the same thing as my second base of 125. But 125 could be rewritten. Okay, this is where using your power chart or just having a base level knowledge of exponential values could be incredibly useful, because you're going to notice something. Okay, 5 to the first is 5. 5 squared is 25. And 5 cubed is 125. So if instead of writing 125, I put 5 cubed, then would both sides of the equation have a base of 5? Aha. So let's leave the first one alone. Okay, 5 to the 4m, that hasn't changed, equals, that hasn't changed. But all of a sudden, let's make this 5 to the third. Okay, because 5 to the third is 125. They are interchangeable. Okay, and then the exponent is still m plus 2. So now, do I have a common base? I sure do. And I just have to use that power of a power property. Okay, so essentially what that ends up doing is saying that this 3 is going to need to get distributed, because we're multiplying, right? We go back and look at that rule. B to the x raised to the y is b to the x times y. So 5 to the 3 raised to the m plus 2 is the same as 5 raised to the 3 times quantity m plus 2. So using the distributive property there, we end up with actually I'll go and I'll make it black. So we got 5 to the 4m, and that equals 5 to the 3m plus 6, distributive property. So now, do I have the exact same base? I sure do. So I can just take those two exponents and set the exponents to be equal to each other. So 4m will equal 3m plus 6, and baby math, take 3m away from each side, and we get m equals 6. Okay, and if you wanted to go through and check that, could you do it? Sure. I'm going to encourage that you go and use probably a big calculator to do it, because I don't happen to know what 5 raised to the 24th power is. Your calculator might even have a conniption trying to go through and figure that one out. But I know that's 5 to the 24, okay? If I go, is that equal to 125 raised to the, what is it, 6 plus 2, 8, okay? So maybe type in 5 to the 24th, okay? Because that's what 4 times 6 is. And then go through and see what 125 to the 8th is. And if those two numbers are the same, then it's going to work out, okay? For some of you, you may get what's called an overflow error with your calculators. So if you go and type this in and it says error, or it just gives you something like overflow, it just means that the number is too big and the calculator's memory can't hold that many digits. So it doesn't mean you're wrong, it just means we got some big old numbers. But if I use my properties of exponents over here and I said, well, 125 is really the same thing as 5 cubed, well, 5 cubed to the 8th is 5 to the 24th. Okay, so is 5 to the 24th the same thing as 5 to the 24th? Yeah, so they got to be equal to each other. All right, dos mas. Now we're going to go take a look at an example where we don't allegedly see an exponent for 1, and we're kind of running out of convenient common bases. Okay, so in example 3, we have 9 to the x, and that equals 27. All right, well, in the first problem, both of my bases were already the same, so I didn't have to use any rules for rational exponents. In the second problem, they were different, but I could write the larger base as a power of the smaller one. So I wonder if that's going to work. Let's try that. Okay, so let's say we've got 9 to the first is 9, and then 9 squared is 81. Crap. 27's definitely not right there. So I can't use a common base of 9. I can't just use the smaller base and a power to make the bigger base. So what the heck am I supposed to do? Well, my suggestion, look for something that the smaller base is a power of, that maybe the larger base is also a power of. I'm looking at 9 and I'm thinking, you're a perfect square, aren't you? Okay, 9's didn't work, but maybe 3's will. Because 3 to the first is 3, 3 squared is 9, and then 3 cubed is 27. So do I have both of my numbers here, 9 and 27, as the same base with different powers? Yeah, okay. And maybe we could also go and look that up on our power chart. Okay, I'll show you guys how to go through and do that after we finish the video today. But let's go through and rewrite this 9 and rewrite the 27. So instead of writing 9, we're going to write it as 3 squared. And instead of 27, we're going to write that as 3 cubed. But everything else about the equation has to be the same. So my first base had an exponent of x. My second base didn't have an exponent. So that's really it. So using properties of rational exponents, I know that 3 squared raised to the x is the same thing as 3 to the 2x, and that'll equal 3 to the third. So now I have a common base. So I can just set the exponents of 2x and 3 to be equal to each other. So x just equals 3 halves. Okay. Could you go and check that? Sure. Use a calculator. Okay. It's fast, it's easy. 9, caret key, parentheses, 3 divided by 2 equals, and you're going to get 27. Okay? Because really what we're doing was we're raising it to 3 halves is we're taking the square root of 9 and then cubing it. Or cubing 9 and taking the square root of that, but smaller numbers are easier. But either way, it checks out. So this is really one other method that we have for when the bases are different, but I can't just rewrite one of them as a power of the smaller one. I can't rewrite the larger base as a power of the smaller base. I have to kind of look further down, a number that's less than 9, but still a factor of 9, to see, well, what numbers are powers of 9 that could also be powers that'll get me 27. Okay, and we kind of come up with 3, right? So let's go through and take a look at one more, because we've done lots of stuff with this property, but we haven't done anything with the fraction, you guys, yet. So, bam, we got a fraction. Okay, so in example 4, we have 1/2 raised to the x equals 16 raised to the 3x minus 1. First thing I want you to do when you see a fraction, don't leave it as a fraction. Make it a negative exponent. Fractions suck to deal with. Negatives, who really cares? Okay, so this isn't really 1/2 to the x. This has got to be rewritten as, and I'll do it in blue. So it's got to be rewritten as 2 to the -1, okay, because that's what 1/2 really is, okay, but you got to write it that way. Otherwise, you end up in like fractional purgatory. So uh, 2 to the -1 to the x equals 16 to the 3x minus 1. So we see here that I have a base of 2 and a base of 16. Obviously, those are not the same. Is it possible for me to write 16 as a power of the smaller base, 2? Well, let's see. If I think about my exponential values of 2, 2 to the first is 2, 2 squared is 4, 2 cubed is 8, getting closer. 2 to the fourth is, yep, 16. So I can use 2 to the fourth as my base instead of 16. All right, so over here on the left, this really just becomes 2 to the -x. That's equivalent to, and we'll say 2 to the fourth because that's how we're rewriting the number 16 raised to the 3x minus 1. We get to do a little bit more distributive property because we also did it over here. And we end up with 2 to the -x equals 2 to the 12x minus 4. So I have a common base of 2, so I can set the exponents equal to each other and get -x equals 12x minus 4. So if I subtract 12x from each side, I get -13x equals -4. And then I can come up with a solution where x equals, what, 4/13? Okay, kind of a weird number, don't you think? Yeah, but does it have to like be one of the same 20 numbers as an answer for every problem? You're not in second grade anymore. No, you're gonna get some weird, funky answers. Okay? Can you check this answer? Absolutely. So long as you leave it in fraction form and you plug it in. You can do 2 to the -1 raised to the, in parentheses, 4 divided by 13, hit enter. Then do 16 caret key parentheses 3 caret key 4 divided by 13 close parentheses minus 1 close parentheses, hit enter, and I bet you're going to see the same number show up on your display again. Okay, so you can always go and check these using a calculator, but the primary solving method that we're using is we're trying to make the bases be the same. Because if the bases are the same, then we can set the exponents equal to each other. In the simplest case, the bases are already the same and I don't need to manipulate them. I could end up in a situation where the bases are not the same, but I can rewrite the larger base as a power of the smaller base. Or I could end up in a situation where neither of the bases are the same, and I cannot write the larger one as the power of a smaller one. Then I got to think smaller numbers and what common factors do they have that I could use exponentially to generate these values, okay? And whether they're whole numbers, whether they're fractional values, rational numbers, all of these you guys can still go through and solve. Okay, so um, right now let's go take a look at the power chart so I can show you guys how you can use that to help you find these numbers.